Well, good day to everybody. Welcome to another Tutor Wizard stream. Today we're continuing with the Introduction to Statistics lecture series. This is number 4. I'm your host. My name is Tim. Nothing new today. What we are going to do, though, is review the calculations and some of the main arithmetic and mathematical ideas that we've seen up until now, including a couple of things I haven't spoken about, but I'm going to talk about today. So this might be a bit shorter than usual. We'll see how the computations go. I don't want to rush through it. I know laying a good foundation for the calculations is very important, but at the same time I also know that everybody has things to do as well. So let's carry on, shall we? So the first idea we're going to talk about, and we've already mentioned this in the past. Let me get rid of that. Go away. Okay, how come that's not going away? Okay, there we go. Now we're good. Is what's the mode? Well, the mode of data is the value that appears most often. In our data set here, that is the values of 15. So this is unimodal data. Whoops, I didn't get that one in the right spot. Right, there we go, unimodal data. Okay, I can't write very well today. And that's entirely because I'm using an older laptop. It's got a screen that's sensitive, of course, but it's not a tablet. So I have to do a bit of a reach thing here. So the mode here is the number 15, because that's the most frequently occurring value in this small data set. And we call this unimodal, because there's only one. Now, let's say there was a case where the data had more than one mode. In other words, more than one value that appeared most often. So ties are allowed. We could have bimodal data. Bimodal might have been the case where we have 4, 4, 10, 15, and 15, because now we have 2 modes. And of course, this can be extended to as many modes as the data has, although after bimodal, we usually just call it multimodal and be done with it. So the idea of the mode is pretty straightforward. It is the most frequently occurring value. That's it. Pretty simple idea. So we won't spend any more time on that. We'll move on. So here's the mean value. Now, mode is just symbolized usually with a word. We don't usually have a symbol for that. But for mean values, it'll be whatever the variable is with a bar on it, typically y bar or x bar. Nothing fancier than that. Just want to check my audio. Make sure everything's working fine. Yes, it is. Okay, good. So to calculate the mean, you've already learned how to do this in school. You add up the numbers and divide by how many. Pardon me. Well, there's a formula for that. So if you're trying to sort out what the formula is, typically on a formula sheet, it looks like this. So I represents an indexing variable. And that's the lower bound. This is the stylized E is the capital sigma from the Greek language. And the upper bound, here it's going to be 4. Oh, sorry, I'm lying about that. There's 5 in this one. My bad. Let's fix that up. We can turn a 4 into a 5 just like that. And indexing variables are written as subscripts. So this is the first observation, y sub 1. This is the second. This is the third. This is the fourth. And this is the fifth. So y bar is the sum of those values divided by how many values there are. So here we would have 7 plus 8 plus 12 plus 17 and 26, which we're going to divide by 4. So what does this add up to? 7 and 8 is 15, and 12 is 27. This is 37, 44, 26. This adds up to 70. And I still have that number 4 stuck in my brain for some reason. I don't know why. We'll put it back to what it should be, 5. So 70 divided by 5 is 14. So this is our average value. In most statistics courses, your prof is going to flip around from speaking about means to averages all the time. So they're synonyms. Just get used to it. There's really no other way to deal with it. Now, technically, if you're doing more mathematics, there's 3 different ways to calculate mean values. There's the arithmetic, well, I cannot talk today. The arithmetic mean, which is what this one is. There's also a multiplicative mean, geometric mean is another way of calling that, and then there's a harmonic mean. But unless you're doing something much more oriented towards mathematics, that really doesn't matter. And I see my audio is a bit distorted here, so I'm going to adjust my microphone a little bit. My apologies if the previous audio was extremely loud. I didn't notice that slider bar had been bumped. Okay, moving on. Now, first thing that's going to be, I see we have ads running. Well, we're going to wait a little bit here before we let the ads run out, and then we'll start the next topic. And we're almost through these. I hadn't noticed this as well. One of my favorite ads, by the way, is the Skip the Dishes ad here. So, yep, well done. Probably because I know most of those people, at least figuratively speaking. I know they're doppelgangers. Now, the weighted mean. So this is a new topic. We haven't talked about weighted means before. Now I want to demonstrate something. If I have 2 data sets, here's data set number 1 and data set number 2. If we've already calculated this one, the average value for the first data set we know is 14. And let's quickly compute the average value for the second data set. So here we have 30, 44 divided by 4, that's 11. So if I asked you, what is the mean of y sub 1, let's not call it that. That's bad notation. What is the mean of data 1 and data 2? The wrong answer is to say, let's add them up and divide by 2, because we already know the averages, right? So this is 25 over 2, or 12.5, but the problem with this is that it's incorrect. The wrong method. The only time that you can simply take the average of the averages is when the data size is exactly the same. Here, N1 is 5, here N2 is 4, so N1 doesn't equal N2, so you can't do the method I just showed you. That doesn't work. Now, when the number of observations is small, the correct way is simply add all the observations and divide by how many. That's the definition of the arithmetic mean. But if there was several thousand numbers, that's probably not the way to do it. or you may not have access to the raw data. So the correct way is what follows here. So this will work in every case, whether you have access to the raw data or not. So the correct method is take the average of the first sample or first data set, multiply it by how many there are, and then we're going to take the average of the second data set and multiply it by how many there are, and then we're going to divide by the total number of observations. So what we're doing really is just a little reverse engineering. Now, and we will verify this too by counting everybody and verifying the mean value. So the first average was 14, and there were 5 of them. The second average was 11, and there were 4 of those. Now, this is 5, and then we add 4. So what do we have here? So this was 70, and this is 44, which should be 114, and divide by 9. So let's find out what that's actually equal to. Where's my calculator? I mean, we could do this longhand. I mean, sure, I could show off and do that longhand, but I'm not averse to calculators, so let's do that. 114 divided by 9 is 12.667. Well, it's triples. It's 6 is repeating out, but that's what it is. So this is the correct average, which is not the same as 12.5. Now, let's verify that we got this right. And really all we have to do is add up the numbers, the observations in data set number 1 and in data set number 2. Well, you'll notice we've already done that. We know from previous work that this thing here was 70. And I just did this one. We know that's 44. Well, there we go. 44 and 70 is 114 divided by 9 is 12.67. It's highly likely that somewhere in this course you're going to have to do that. And it's highly likely that it's going to be on a midterm exam as well. So you don't need to worry about it too much. Just remember that when the sample sizes are not the same, you have to do the weighted mean method. And that's what we have right here. Okay, clear as mud, I can tell. Let's move on. Now we have variance. Now I'm going to do both computations for variance. You'll notice here I have s squared, and here I have little sigma squared. This is the sample variance. I'm just going to abbreviate that as sample var. It doesn't look like a var, does it? No, it don't. Let's get that out of there. Try again, Tim. And this is the population variance. What's the difference between the two? Well, you divide by either n or n minus 1. So I'm going to write both formulas down here, and then we'll go to a new slide to do the computation because I'm pretty sure I can't make it fit here. So first off, I want to copy that data. Give me a moment to do that. We'll do that. That's not what I wanted. Got too much. Okay. Trying again. There we go. Boom. There we are. Control C for copy. Cool. All right. So population variance. That's going to be little sigma squared is equal to the sum of the observations from 1 to however many there are, and we need their deviations. So each observation minus its mean value squared divided by how many. So for population variance, the astute amongst you may recognize that this is simply the average deviation from the mean. And then you'd be right. But we don't talk about it that way too much. It's unnecessarily precise. Sometimes unnecessary precision for people just learning a topic leads to confusion. So we're going to talk about it as simply the spread of the data. Now, what is a sample variance formula? Well, it looks pretty much like the one we just wrote with one change. We still have y sub I minus y bar squared, but now we're dividing by n minus 1 the degrees of freedom, which we talked about in a previous video. All right, there's our formulas. Now let's compute them. We'll need a new slide for that, though. We'll add a new page, and we'll paste in the data so I don't have to try to remember it. All right, let's get sigma first over here. So here is little sigma squared. And let's label this. This is y sub 1, this is y sub 2, this is y sub 3, y sub 4, and y sub 5. And we know that y bar was 14. All right, we have what we need. Let's do this. Now, we need, let's write the formula, 1 to 5 in this case, y sub I, y bar squared divided by n. So let's expand that. So this is going to be, in brackets, y sub 1 minus 14 squared. And then we have y sub 2 minus 14 squared. Anybody with a decent calculator, and it doesn't have to be a graphing calculator, by the way, anything that has a statistical function on it will do this for you, so you can always check. Y sub 3 minus 14, y sub 4 minus 14, and y sub 5 minus 14, and you'll notice those are all squared. And we're going to divide by how many? Well, how many are there? There are 5. Let's carry on. So this is 7 minus 14. This is 8 minus 14. This is 12 minus 14. And we have 17 minus 14. And finally, 26 minus 14. And again, divide by 5. Now, 7 minus 14 is negative 7. I want to make a point about something, so I'm not going to square that just yet. 8 minus 14 is negative 6 squared. 12 minus 14 is negative 2. Then you'll notice this flips to positive. This is now positive 3. And this monster over here is positive 12. And we divide by 5. Now, it's a characteristic of many computations in statistics, specifically, or in particular this one, that the sum of the unsquared deviations is always 0, unless you've screwed up. So that's why I delayed doing the squaring. You'll notice that this is negative 7, negative 6, and negative 2. So we have negative 15 for values smaller than the mean. Here we have positive 3 and positive 12 for another sum of positive 15 values greater than the mean. These things cancel out. This cancels to 0, as it should. But of course, zeros are terrible when it comes to doing actual mathematics, so we square them to get rid of them. In many ways, we're just finding the absolute values here, but we'll talk about that in more detail at another time. All right, negative 7 squared is 49. Negative 6 squared is 36. Negative 2 is 4. This is 9, and this is 144. And we're still dividing by 5. Now, what does this add up to? Now, I haven't pre-computed this, so we're just going to wing our way through this. So this is 40. And this makes for 89. This makes for 108. 208 And looks like 252 to me. I'll use my calculator in a minute. I just like to keep the brain rust out by doing math in my head. So this is going to be 50.4, unless I've screwed up. But we're going to check and see if I did or not. Now, you're saying, wait, that's pretty darn big. But remember, this is a result of squares. None of the deviations in the actual data set can possibly generate a value this large unless we're working with squares, which is why when we move to the business of standard deviation, we'll take the square root of that, and this will come back into appropriate magnitude. Let's just check the math, though, really quickly. And what do we have here? This was 7, and then we had an 8, and then a 12, and a 17, and a 26. Boom. Now we just got to get the population variance. And I think we have to hunt for that on my calculator because I was just typing the command in there. And apparently I typed the wrong command. So we'll just do it this. There it is. Got it. Okay. So apparently I made a mistake. It should be 48.4. How'd I screw that up? Okay. Should have been that times by 5. So it should have summed to 242. So apparently I made a mistake adding up the numerator, which is why we always check. Everybody makes mistakes, and you just saw a doozy right there. I never get 100% on anything because, I'm overconfident and I go fast and, well, silliness. Let's just check here. So we had 36 and 4. That makes 40. And then we had 49. That's 89, not 99. Okay, well, whatever. And then we have another 9 and 144. 9 and 9 is 18, and 4 ends in a 2. Carry the 2. That's 10. 4, carry the 1. 242. Okay. So this is going to be 48.4. This is why we check. And it's okay to do it by hand. Nothing wrong with that. Anyway, this is called the population variance. In most introduction to statistics courses, we don't usually do this one because we're very focused on analyzing sample data, which is what we're going to do on the next page. So let's do that. Let's move over. I'll add a new slide for that. So now we want sample variance. Sample variance. Okay, let's pop the data in so that we can reference it. There it is. Now, what is the formula for that? Well, the formula for the sample variance, getting tired, I'm going to leave it in red today. I kind of like red. All right, so sample variance is lowercase s squared. And much of the numerator, well, all the numerator is unchanged. So we're going to go from that. And this is going to be y sub I minus y bar squared, just like before, but now we divide by n minus 1. There's a theoretical reason for that. I don't think we'll probably talk about that in this course, but we'll see. Maybe sometimes it's nice to talk about more complicated topics, but not too early in a course. Now remember, this is y sub 1 right here, y sub 2, y sub 3, y sub 4, y sub 5. Because this is basically the same computation, I'm just going to write it out. So we had 7 minus 14 squared. And we have 8 minus 14 squared. And we have 12 minus 14 squared. 17 minus 14 squared. That's supposed to be a square, by the way. And 26 minus 14 squared. So nothing's changed there. But now we're dividing by 4. That's what's different. So if we do the numerator just like we did before, this will be 242. And we're going to divide by 4 this time. Now what does that give us? Well, that's going to be 60.5, I would say. We better check. I was wrong last time. Might be wrong this time. Let's find out. All right, let's go. Come on. Why is my calculator being bulky here? There we go. I use the TI Inspire series of calculators because I like to ask my calculator to do interesting things, and that requires something with a lot of horsepower. All right. We just got to change that pop to var. Sample. What? That's not right. Okay. This is annoying. Okay. Trying again. And let's get that. Let's try this one. I'm looking around here. There we go. Variance of the sample. And it's 60.5, and this is the correct value. Now there are some formulas that we're going to encounter in this course where we work with variance, sample variance specifically, but not too many. Most of them are, yes, we're going to use sample variance for most of them. It's the population variance we won't use a great many instances of, but it's nice to know how to compute both. Let's move on. Next slide. So now we want the standard deviations. Well, the standard deviations are simply the square roots, or in other words, the absolute values of the deviations. Now I want to draw a picture to explain this before we do the mathematics. What do I mean by deviations or deviations from the mean? And I'm going to show you. So first off, we need a line, and I'm just going to make a number line because that makes things easier to talk about. Okay, so on this number line, we're going to put in the average. Remember, we know the average of this data set is the value 14. So let's put that right there. All right, so this is y bar 14. Now, what is y1? Well, this is y sub 1 right there. So that's our first observation. It's at 7, so 7 is smaller. We'll put it over here somewhere. So here's y sub 1, which is number 7. And the difference between these two values is negative 7. This is a deviation. Now let's go back and show you something about that. 7 minus 14 was our first deviation. If we go back here, we see that was negative 7. So that's why we call it standard. We're basically finding an average, standardizing the deviations of each observation from the mean value. Let's put the rest of them in here. So this is y2. It's at 8. We'll put that over here. So this is y sub 2. It's 8. And its deviation is negative 6 units. And then we have y sub 3, which is pretty close. It's over here. We'll call this y sub 3. Its deviation is only negative 2. So you'll notice, that's not negative there. Here's our negative 7, our negative 6, and our negative 2. So the total deviations that are smaller than the mean sum to negative 15. There are two values bigger. One is at 17. So this was y sub 4. Its deviation here is plus 3. And then way over here is y sub 5. Its deviation is huge, and that is plus 12. So our total of our deviations here then is the positive 15 that we talked about before, and that plus this equals 0, as it should be. So when we talk about deviations, we're talking about deviations from the mean. The computation for this then, for the population standard deviation, which is just lowercase sigma, is the square root of the variance. And I'm just going to abbreviate that as pop var. Now, the astute amongst you may recognize this as simply saying the absolute value of the deviations. That's really all it is. The square root of a squared sum, absolute value. Okay. Anyway, so sigma is going to be, I'm going to draw this out the long way. So here we're going to have an n. Here we have I is equal to 1. We have y sub I minus y bar squared divided by n. Maybe a little bit too ambitious on that. Let's get rid of that. Boom. Well, this is one way to write the formula. But this is a handy way as well. Either way, we want the square root of 48.4. Now, what is that? Well, it's going to be a bit more than, or pardon me, just a little bit less than 7. I'd say it's going to be about 6.95. Let's go with that. So we have 48.4. And we get 6.957. This is our standard deviation. And if you look at the size of the deviations, here is -7. Here's -6, -2, +3, and +12, then this number, as far as its magnitude goes, fits right in to our diagram. It's the right size, as opposed to that very large squared value we had earlier. Okay, let's add another slide and do the sample standard deviation. So here's our sample standard deviation. So this one you're going to work with a lot. Now I'm not going to reproduce the picture. It hasn't changed. It's not going to change. This is going to be s, which is simply the square root of s squared. I always put a little vertical bar like that on my square root symbols, the radical symbol, simply to say this ends here, because sometimes it's a bit ambiguous if you're writing things in a hurry. So this is going to be the sum of the deviations. yi minus y bar squared over n minus 1, all under a square root. Now, we know from earlier that that was 60 point something or other. Let's go back and have a look at what that was. 60.5. So we need the square root of that. Now, the closest square root, perfect square root, is the root of 64, which is 8. So this has got to be about 7 point something or other. I'm going to call it about 7.7. 7.7 seem reasonable? Let's find out. 60.5, and we want the square root of that. 7.778. There we go. Now, you'll say, wait a minute, that's a bit bigger. That's right. One of the things you'll find when we're working with this stuff, this kind of computation, is the fact that we're working with a sample means we're less accurate. Although the larger the sample, the more accurate we're going to be. That's a truism in statistics. Small samples lead to less accurate results. Now, remember we're dividing here. So as we divide by bigger and bigger numbers, the overall value gets smaller and smaller. For instance, 1 over 10, that's just 0.10, but 1 over 100, 0.01. Well, if I go 1 over n, but I let n go to infinity, I can hear the calculus people going, yes, limits, then this becomes 0. So there's a trend here. You'll notice that? All right. We're going to talk about what this implies for the spread of a data set when we get a little bit further into the course. And I don't want to steal that. It's a trip off into the ditch right now. We're not going to go there. But the point is, there's some interesting stuff coming up on how the measurement for spread changes as the sample size gets larger and larger. Delta function, anybody? All right, moving on. Okay, enough of that. It's the median and quartiles of a data set. Again, we talked about median and quartiles in an earlier conversation. Just want to review this quickly. Remember, median is the exact center. It is where you have 50% in the lower bound and 50% in the upper, I shouldn't say bound, in the lower half of the data and 50% in the upper half of the data. And quartiles then means we're quartering the data. I didn't really talk about that in that context last time we discussed this topic, so I'm going to do it again. I'll do it a bit more detailed this way. Quarters. There we go. 25%. All right. So we have a median, which is the exact center. So here n is 5. It's an odd number. So this is the median value, which we can also call Q2 if we wanted to, and we sometimes will. So the median is 12. Now in this course, and in most courses, this isn't the only way of doing this, and I will talk about the other way at another time, but for what we're doing here, the median of the lower half is Q1. So Q1 is 7.5, because we would go 7 plus 8 divided by 2, which is 15 over 2, and hence 7.5. Then that means right here must be Q3. And what is it? Well, it's halfway between 17 and 26. Well, those two numbers are going to add up to an odd number, so of course we're going to have a fraction. 17 and 26 divided by 2, so that's 3643 over 2, so that should be 22.5. Boom. And this, of course, is associated with the 5-number summary, which we're going to get to in a moment. But when you're quartering data, then, what do we have? Well, let's break this up like so. And maybe using a box isn't the best way of saying things, because it'll confuse with the box plot, but that's fine. The point is we have 25%, 25%, 25%, and 25%. Where does this happen? This happens at 7.5. This one is at 12, and this is at 22.5. That's how we break this up. The interquartile range, which you're going to talk about coming up, is simply the center, 50%. We'll get to that. How are we doing on the clock here? Well, we're doing all right. All right, moving on. Oh, by the way, before we move on, quartiles is just a handy way of breaking data into 4 equal chunks. You can have deciles, where you break it into 10 equal chunks, and percentiles, which is 100 equal chunks. And if you ever had anything to do with babies and going to health clinics and get their weight, oftentimes, oh, your child is in the 95th percentile. We're going to talk about that, but in a different way. It's coming up in the course. So we won't be trying to cut this stuff into slices that fine. We'll slice it up later. The numbers, that is, not the babies. Okay, what is the interquartile range? Well, I just showed you that. It's the center 50%. But if we wanted to, we could turn this into the box plot. So this is similar to what I had earlier. I said, wow, that's just going to be confusing. I didn't mean it to be. But so here, the interquartile range is the center 50%. Let's go back here for a minute. My lower bound was 7.5. My upper bound is 22.5. So this one clearly has a skew. This is 7.5. This is 22.5. Now, the median is much closer to the lower bound than the upper bound. This was 12. So this is the bottom 25%. This is the first 25%. So if someone said, what's the boundary of the lower 25% of the data set? Well, it would be 7 to 7.5. Because 7 was the minimum, right? And then the next 25%, which would be from 25 to 50%, I don't have room to put it in there, we'll do it this way. Well, that ranges from 7.5 to 12. And then we're going to have the 50th to 75th percent. Well, that ranges from 12 to 22 and a half. And then this will be the 75 to 100%. And the maximum value for that was, I don't actually remember what that was. It was 26. I don't know why I can't remember that. So 22.5, and this was 26. So this is how box plots the interquartile range and the 5 numbers summary all play out. Now, what is the 5 numbers summary? Well, we've already written it. It's all here in this picture. What is the minimum value? Well, the minimum value is 7. What's the next interesting value? The first quartile. That was 7.5. Then we had the median, or Q2 if you wish. That was at 12, followed by Q3, which was 22.5, and the max, which was 26. So everything here is here. Perfect. The only thing remaining to show here is how do we compute outliers? Is 26 an outlier? Is the number 7 an outlier? So outliers are numbers lying beyond the fence. So these are values that lie beyond the fence. And how do you calculate the fence? Well, that's easy. The upper fence is simply Q3 plus 1.5 times the interquartile range. Now, sometimes we want to be more discerning about the magnitude of the outliers. Most of the time we don't talk about them like this in this course, but just in case your course does, multiplying by 1.5 gives you a mild outlier. If this multiplier here was 3.0, then we would call that an extreme outlier. But generally that gets discussed in another course. All right, Q3 was 22.5. Our multiplier is 1.5, and our interquartile range is 22.5 minus 7.5, so that's 15. Or it better be. Now, what's 15 made larger by 50%? Well, that's actually kind of interesting. I didn't plan it this way, so Q3 is 22.5, and 1.5 times 15 is also 22.5. And this adds up to a whopping 45. So that means any observation greater than 45 is the upper fence, which we don't have. 26 is the maximum, so there is no upper outlier. And if you want to double check that, let's just check this. Here we have 15 times 1.5. 5 times 5 is 5. Carry the 2. That's a 7. This is a 5 and this is a 1. We add that up. We get a 5 and a 2 and a 2. 22.5. Yay, me, I win. All right, let's do the lower fence now and see what we get. We need a little bit of wiggle room, though. Let's give that a little bump. What was the lower bound on that thing? It was 7.5, yeah. Pretty sure there's no lower outlier either, but we'll do this to be complete. So the lower fence, now remember, anything beyond, smaller than the lower fence will be an outlier. That's going to be Q sub 1 minus 1.5 times the interquartile range. We've already done those computations, so we'll just copy them down. Q1 was 7.5. This is 22.5. So this is negative 15. Well, we don't have any negative numbers, so there are no lower outliers. Boom. And that's really all there is to it. Box and whisker plots are very easy to use. And they tell you a lot. For instance, we know that, well, here, let's move this up a little bit. From a previous discussion, I said if we had skewed data, a right tail skew is present when the mean value is greater than the median. Well, earlier this data set had a mean of 14 and the median is 12. So this is what I meant earlier in a previous lecture when I said we compare the mean to the median, we can tell if we have a skew or not. So if we were to try to, we only have a few data points, so it wouldn't be much of a smooth curve, but it basically looks like that. Here's your median, and here's your mean, because this is 0 and this is infinity. There we go. I think we've talked about that enough. Let's move on. We're done. Next time. What are we doing next time? Next time it's contingency tables, which are very useful, and we want to have a reasonably good understanding of them because then we can use them in probability as well. So, there we are. Thank you for joining me today for lecture number 4 in our series for Introduction to Statistics, kind of laid out for spring intersession courses at most post-secondary institutions. Remember, this doesn't have to be a terribly hard course. There's a lot of content, of course, but in most places that let you use a formula sheet and a calculator, so don't fear that. The only thing with summer classes, of course, is they go by very quickly. So I'm going to try to keep a fairly steady pace so that what I'm doing is fairly well aligned with the material you're seeing in class. So if I'm a day or two ahead or a day or two behind, it should all work out towards the end. Anyway, thank you again, and I'll see you next time. There won't be a stats lecture tomorrow, 24 hours from now, but I'm planning one for 2 days from now, which, well, today being Saturday, of course you can watch this whenever you want, but trying really hard to stay away from that. But there should be another one up in about 48 hours. Anyway, let's call it there. Everybody have a great weekend. It is the weekend today, but it may not be the weekend tomorrow. This streaming stuff is hard when you're old. Anyway, have a good day, and we'll see you soon.